Okay.
Welcome all. Welcome to Papers We Love, Los Angeles. Thank you for coming. I hope you all enjoyed the pizza drinks. And first timers, good to have you here. I hope to see you again. We're in for a treat tonight. Thank you to Yahoo for hosting us this month and providing us with food and drinks and AV equipment. So I'll hand it off to Paul, but we are always looking for presenters, and we are always looking for places to hang out. So if you would like to do either, I would like to talk to you. So let's give a hand to Paul.
Well, thanks everyone. Thanks for coming. I hope this is as fun for you as it is for me, but to be perfectly frank, I doubt it. So the paper is Propositions as Types. Philip Wadler should have put his name on here. I don't know how many of you have actually read the paper, but it's pretty short. It's about 17, 18 pages, and really lays out in sort of nice summary form the relationship between formal logic and types as in statically typed programming languages. So let's go right ahead and dig into this. Dr. Wadler says that this notion, this propositions as types notion, is a notion with depth because it establishes a one-to-one correspondence between any given logic and any given type system or any given typed programming language. So, you know, what do we mean by that? First of all, what do we mean when we say a logic? Do we mean this? Reasonable question. Those of you who are familiar with Mr. Spock, which I hope is everybody, are probably aware that his approach to logic is very informal, is very you know, based on sort of an intuitive notion as to whether something makes sense or not. And in fact, I would argue that sometimes his claims that something was illogical were mistaken. But that's not actually what we're talking about, as Dr. Wadler points out. He says that what we're really talking about here is formal logic, and formal logic is essentially a language in and of itself. It has a syntax, it has a semantics, and so on and so forth. Logic in this sense has actually been around for a very long time, thousands of years. If you just talk about Western civilization, which is the only civilization I'm familiar enough with to talk about, you can take that all the way back to Aristotle and the ancient Greeks and all that, Euclid. But where it really takes form as a structured thing with a syntax, in particular, is the 19th century. And interestingly enough, for those of us who happen to write software for a living especially, one of the big names in the 19th century here is George Boole, yes, that Boole, as in Boolean, right? So we talk about Boolean algebra, which is kind of funny because if you actually read Boole, most of what we talk about when we talk about Boolean algebra and programming bears very little resemblance to the full flavor of what Boole wrote about. But anyway, there are all these folks actually in the 19th century who put their minds to answering the question as to how do you reason soundly, and then once you've figured out how to reason soundly, how do you express that in language? How do you express that unambiguously in particular, which is kind of the point of having a syntax and a semantics and all that sort of stuff. So a lot of good work here in the 19th century on logic, formal logic. But what's the point of all this? And again, Dr. Wadler spells it out in Hilbert's program, right? So Dr. Wadler points out that one of the things we're trying to do is we're trying to describe the process of reasoning. We're trying to describe the process of maintaining truth. We're trying to describe the process of having information and drawing conclusions from that information. And one of the Hilbert came up with this program, and one of the pieces of that program was what's called the Entscheidungsproblem, which is basically the decision procedure or search for a decision procedure to determine, given any logical statement, can we determine by some well-defined, rigorous, repeatable process whether it's true or not? And this was a question around the end of the 19th century and into the 20th century. Okay, and then finally we get to the early 20th century, actually not that early, into the 1930s, when people following Hilbert's program were trying to answer these questions that he posed. And a bunch of logicians in the 1930s were tackling this problem with their, with all their intellectual might. And here we get to some of the giants of formal logic in the 1930s, and we start to get into what we now think of as computation. But this was a very new idea in the 1930s, in the mid-1930s, of course. And here we see some names that are probably fairly well known if you are into computing at all, in particular Alan Turing, of course. But other names that should also be as familiar, or possibly more familiar: Alonzo Church, Kurt Gödel, and Stephen Kleene, all of whom came up with definitions of what it means to compute something. And it might seem kind of weird that it took until the 1930s to arrive at some rigorous answers as to what it means to compute something. But it did. If you read Turing's paper, in which the Turing machine is established, when Turing uses the word computer, he's talking about women with pencils and paper. That's what he meant by the word computer. And so what he was literally trying to do was to say, if you were to take this process that a human being with a piece of paper and a pencil does, and the reason I say women with pencil and paper, by the way, is World War II and Bletchley Park and code breaking and all that kind of stuff. I'm not trying to be sexist. That's literally what was going on. If you take that human process of sitting down with a pencil and paper and working through a computation, a derivation of something from a piece of information to another piece of information, and you wanted to make that repeatable, in particular, you wanted to have confidence in the result, how would you define that? And we came up with these three definitions of algorithm, as it turns out, in the 1930s. Even though, as Dr. Wadler points out, that concept certainly goes back to Euclid, goes back to al-Khwarizmi, which is where the word algorithm comes from, and so on. But it didn't get rigorously defined until these folks did that in the 1930s. So, let me go back a step. One of the three definitions of what it means to compute something is called the lambda calculus. And that came from Alonzo Church, and it was originally intended by Church as a formal logic. In fact, it was supposed to replace the logic found in Russell and Whitehead's Principia Mathematica. So the basis of this definition was as a logic, not as a tool for computation at the time. Okay, now moving on. Lambda calculus is logic. Okay, so logical soundness, you're supposed to put truth in and get truth out, right? And by the way, it's been understood for millennia that if you start with a false proposition, you can prove anything. And that's called inconsistency. So if you're trying to come up with a formal logic, you obviously don't want it to be inconsistent. You don't want it to be able to prove anything from anything. Right? So this was a problem for the lambda calculus. Two of Alonzo Church's grad students, Stephen Kleene and John Barclay Rosser, proved in 1936 that the lambda calculus is in fact inconsistent. The untyped lambda calculus is inconsistent. So boom, there you go. You can't use it as a logic. You can prove anything with it, unfortunately. But in the process of investigating it, they also noticed that lambda calculus was pretty interesting all by itself. It had its own, it had its own interest. It's like, there's something going on here. Church couldn't quite figure out what it was at the time in his first paper on lambda calculus, but he was aware that there were reasons to be interested in the lambda calculus other than its use as a logic. But then his grad students were like, yeah, well, it's useless as a logic, so let's hope that it has other uses. Well, it turns out that it does, and so here we come to a fork in the road, and Dr. Wadler does a great job of explaining this. And the fork in the road is basically that you've got an inconsistent logic, but nevertheless, we have these other definitions of computing, including the Turing machine and recursive functions from Kurt Gödel. And they're all equivalent. And it turns out that literally anything you can do in one of them, you can transpose and do in the other, all three of them. And they do completely describe and define what it means to be computable, even though, as a logic, lambda calculus is inconsistent. Now here comes the funny part. The proof that Kleene and Rosser came up with to demonstrate that the n-type lambda calculus is inconsistent is very famous in Lisp and scheme programming. It's called the Y combinator. It's how you define recursive functions without naming them. And so, in other words, it's how you sneak self-reference into the lambda calculus or into scheme. And so I love this picture of somebody with the Y combinator tattooed on their arm, because this is sold in programming as a great thing. This is how you do recursion. This is how you do general recursion in the lambda calculus. Well, guess what? That's the very thing that makes the lambda calculus inconsistent as a logic. It's a disaster. Okay. So people go around getting this disaster tattooed on their forearms.
You say you are lying, but if everything you say is a lie, then you are telling the truth. But you cannot tell the truth because everything you say is a lie. But you lie, you tell the truth, but you cannot, for you lie. Illogical, illogical. Please explain. You are human. Only humans can explain the behavior. Please explain.
I am not programmed to respond in that area.
So it turns out Captain Kirk understands the Curry-Howard isomorphism perfectly. And as Dr. Wadler points out, the parallel is, in logic, if you have inconsistency, then in your programming you have an infinite loop. Or you have a core dump, or you throw an exception, or because what it means to be logically inconsistent is that you can't actually provide an answer. You can't actually answer the question. There is no answer. There is no way to get to the end of this process, and so this process either never ends, or you just bail completely in some horrible physical sense, like dumping core or throwing an exception. I just love this particular clip, of course, where we have, a popular exposition of the Epimenides paradox. Everything I say is a lie. So if I'm telling the truth, then I'm lying. If I'm lying, I'm telling the truth. And that actually does drive computers nuts, or I should say it drives any formal logic nuts, which by the Curry-Howard isomorphism drives programs nuts. Okay, so logic and computation got a divorce at this point. This quote from Dr. Wadler says pretty much everything there is to say on the subject. They're mutually exclusive in some sense. And so the problem is that you either have something that can express anything that can be computed at all, in which case you have inconsistency and you have an unsolvable halting problem, or you have something that can't actually express anything that can be computed at all, but it has a trivial halting problem. Everything halts. By the way, for those of you who are familiar with the notion of function, whether from set theory or some other subject, you might recognize here that we're talking about total or partial functions. A total function is a function that's defined for all elements in its domain. You'll get something in the codomain out of it. That's a total function. A partial function is something that's not necessarily defined for all elements in the domain, and then what? You don't get anything out. You get an infinite loop, or you get a crash, or whatever. Okay. So the structure of proofs. So formal logic, 19th century, moving forward into the 20th century, again in the 1930s, a guy by the name of Gerhart Jensen came up with a couple of syntaxes, if you will, for formal logic. And one of the things he noticed is that these logical rules come in pairs. And there's this notion of an introduction rule where you introduce a connective. And there's a notion of an elimination rule where you eliminate the connective and arrive at a conclusion. And so there's this kind of duality between introduction rules and elimination rules. And this becomes important in just a few moments. By the way, that sort of sideways U thing means implies, for those of you who are unfamiliar with sort of 19th century logic syntax. We'll see more of that in a bit. The Curry isomorphism, half of the Curry-Howard isomorphism, which, by the way, is probably the more popular name for propositions as types, at least in the type theory world. the Curry-Howard isomorphism. So the Curry isomorphism is basically that. This was recognized by Haskell Curry, by the way. For those of you who don't know who Haskell Curry is, obviously the Haskell programming language gets its name from Haskell Curry. There's also, by the way, a Curry programming language that nobody uses. Even fewer people than Haskell. So it's the truth. Sorry. I love Haskell, don't get me wrong, but it's a minority position. So Haskell Curry observed, again in the 1930s, that there is this one-to-one relationship between the notion of a function which takes a value and returns another value in some computational process, and the notion of logical implication, where you have a proposition that implies some other proposition. And it turns out you can go back and forth between those two at will, in a certain kind of logic, which is called a constructivist or intuitionistic logic. I'm not going to go into that in any detail because that would take us way too far afield, but it is in Dr. Wadler's paper. The Howard isomorphism, and I have to say, this is where most of the oomph comes from. Curry had kind of an inkling in the 1930s, but it's really Dr. Howard who dotted the I's, crossed the T's, and filled in a bunch of the blanks. So not only is there this one-to-one correspondence between logical implication and a function that takes a certain value of a certain type and returns a value of another type, but it turns out to work for the other logical connectives too, and or not, all that sort of stuff. And quantification. I think I have that in another slide. Conjunction. Right. So Dr. Howard observed that the notion of logical and, conjunction, is isomorphic to the programming notion of a record type, or any type where you have multiple values of different types that are kind of glued together. So record types, tuples, whatever you want to call them, any structure in which there's more than one value at the same time, right? You have this and that. Simple, right? I mean, this is one of those insights that's kind of obvious once it's exposed to you. It's like, yeah, this is ridiculously simple, as all good ideas, I think, in the end are. Disjunction, or, logical or, this or that. Turns out, surprisingly, a lot of programming languages still don't have the corresponding type here, which is called a sum type, or sometimes a disjoint union, or I forget what some of the other terms are. But anyway, it's the notion that you have either this value or that value, but not both at the same time. Being a Scala programmer, of course, for me, this is either or. Actually, there's a type in the Scala Z library called disjunction, which actually looks like the logical disjunction, and we'll see some more of that later. But there is, again, this correspondence between the notion of logical or and a type in a programming language that represents a value of this type or a value of some other type. Implication, yeah, we talked about this already. The idea that logical implication and function type are isomorphic. This implies that. They even both use arrows. Typically, when you have a functional programming language, the function type is A arrow B. In logic, it's just a different kind of arrow, syntactically. Quantification and dependent types. Yeah, this is probably Dr. Howard's biggest contribution to the field. He noticed that the logical quantifiers for all, and there exists, map onto a notion that nowadays is called dependent types. I'm not going to spend a lot of time explaining those, but suffice it to say that dependent types can depend on values. So the popular example, overused example, but lends itself to intuition, I guess, is some sort of container of a fixed statically defined size, like so a vector of 5 integers or something like that, where 5 is actually part of the type. Vector of 5 integers is a type. That's a dependent type. And those kinds of types correspond to for all and there exists, and we'll talk a little bit about that, but not a lot. It's a bit much. Quantification and type abstraction. So here we get a little deeper into polymorphic lambda calculi, where you have the power to say, as I think we pretty much all do over the past decade plus at this point, I have a type that's defined in terms of another type. The obvious example, of course, is containers, right? You have a container that contains some other type. Dr. Wadler is a little bit too modest to point out that when he says that the design of generics in Java is based on this, he's too modest to point out that that's because he did it. By the way, he and Martin Odersky, actually the designer of the Scala programming language, were co-designers of a language called GJ, generic Java, which led to the design of generics that showed up in Java 5. Quantification and data abstraction, yeah. This is actually interesting to me in the context of cryptography, because in cryptography, you want to be able to say something about something else without giving away what that something else is, right? So you want to be able to say there exists some value such that this property, that property, the other property are all true, but I'm not going to tell you what that other value actually is. You just want to be able to say this value exists, and you want to be able to prove things about that value without giving that value away. And it turns out that quantification and therefore dependent types are super useful in that regard. And again, not going to expand on that. If we want to dig into that in more detail later, we can. But probably offline, because I don't have any of the relevant materials with me. Universality, yeah. So this is where it actually starts to get philosophically interesting. Dr. Wadler's point here is that we have a history here, a clear history, of two people in somewhat different domains, especially back in the 1930s, coming up with the same concepts at the same time. And typically, it's a logician and a computer scientist. And so what that leads Dr. Wadler to observe is that there appear to be, to some extent or another, objective universal truths about logic and about programming language design. And in particular, because it took simple type theory applied to the lambda calculus to make the lambda calculus logically sound, that would seem to justify, and certainly does justify to me, the use of statically typed programming languages. Why? Because I like for my software to be logically sound. That's not to say that if you use a dynamically typed language, you're guaranteed to have a logically unsound system. It just means your compiler isn't going to help you demonstrate that it is not logically consistent. And that's, here's why you have to make a confession. I spent a lot of time programming in Lisp. My name is in the acknowledgments of Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp. Peter Norvig's first text is in the acknowledgments of The Little Prover, Dan Friedman's most recent book. I've spent a lot of time with Lisp and Scheme and all that kind of stuff. And somewhere along the line, I discovered statically typed functional programming, and the rest, as they say, is history. And I didn't understand why. I didn't understand what, I made the transition without really understanding what appealed to me about the transition until I learned about propositions and types. And then it's like, oh, of course, now I know why it is that I respond so strongly to this field, of statically typed programming languages, and especially statically typed functional programming languages. Other people probably feel differently, but Dr. Wadler provides some justification for feeling like, yeah, this is actually objectively true. This is objectively valuable.
Excuse me?
Yeah.
You mentioned a paper on the previous slide. There's your middle bullet,
Oh, yeah.
Reasonable effectiveness of mathematics and the natural sciences.
Yep.
Do you know there was a follow-up paper called The Unusual Effectiveness of Logic and Computer Science that was based on that paper?
I don't think I've seen that, but Dr.
Harper was one of the, Robert Harper and Moshavardi, one of the authors, but they used that paper. It's kind of related to what you're talking about with logic.
As motivation.
Yeah, they noticed that same connection.
Yeah, it is interesting. I do sort of feel like the physics community has a much better handle on why mathematics has this kind of universality to it than computer science does.
Computer science uses logic rather than mathematics. That was the point of the second paper.
Yeah. But that's been an artificial distinction at least since Frege. The idea that mathematics and logic are distinct disciplines is false, categorically.
Is it? Okay.
But I mean, people still think that way, and I'll have more to say about that in a later slide actually as well. But yeah, that's a good point. The M word, yeah, sorry, it had to be done. Or rather, Dr. Wadler did it, so I had to. Dr. Wadler points out that monads are a way that several important aspects of programming language semantics are brought into the realm of propositions as types. And that's true, but I almost think that Dr. Wadler understated the case here. He didn't sort of spell out in explicit detail that monads model I/O and state and things like that in mathematical terms, so that you can reason about them with the same intellectual tools that you use to reason about things that aren't doing I/O or manipulating state or whatever. And this is a huge motivation for those of us who do purely functional programming, whether it's in Haskell or Scala or something else, to care, to care about monads in particular, because it's a reasoning tool. That's what this is all about at the end of the day. Reasoning about your code without having to run it, and having spent literally decades of my life not being able to reason about my code without running it. I just find this unbelievably liberating. Future foundations, yeah. So Dr. Wadler points out that as we look into the future, we look into current research on this notion of propositions as types. We find things like homotopy type theory, I guess that's the second bullet here, and category theory, yeah, of course. For those of you who are familiar with functional programming at all, you probably are aware that a lot of these concepts, like monads, come from category theory, or in another form from abstract algebra. You don't even necessarily have to go all the way to category theory. But it is helpful if you actually want to explore the relationship further between formal logic and programming language theory and programming language design, again, especially type theory and functional programming. Homotopy type theory, that I think, what can I say about that? In another 100 years, I think nobody will be talking about set theory anymore, and probably there will be much less conversation about category theory, because homotopy type theory subsumes both of them and covers new ground and covers it in a computational way. So a lot of the stuff that we find in all of mathematics and so forth that is derived from set theory, from basically Cantor at the end of the 19th century, will probably have been swept away in another 100 years. That's my prediction. So I'm going farther than Dr. Wadler is. None of this, here are Dr. Wadler's comments. I'm expanding on them with my own personal opinion at this point. So what does this have to do with programming at the end of the day? Well, since I'm a Scala programmer, I kind of decided to throw up a little code from a library called Shapeless, where we actually have definitions of the logical connectives in the type system. So we have and and or, complete with their wonderful Unicode symbols that you either love or hate. And we have the universal and existential quantifiers. Those are a little interesting for those of you who don't know Scala. Scala already has existential types. That's why you can say for some. So you can say something is true of some other type, that we don't know what it is. There is some type, it exists. That's why it's existential quantification, right? There exists some type for which this property is true. And then Scala doesn't have universal quantification as part of its type system, but it doesn't have to, because you can define universal quantification in terms of existential quantification. So for all just means it's not the case that there exists some x for which p is not true. Oh, and negation, not, I should point out explicitly, not is simply something implies nothing. In this case, it's a function type taking something to nothing. Nothing is logically equivalent to false. It's an uninhabited type, sometimes called the bottom type in other languages. But it's called nothing in Scala, and it's just a type that has no values, so it logically represents false because it has no proofs. Again, going back to propositions as types, you sort of get used to hopefully, I do, I have, get used to looking at everything through the propositions as type lens. So when I see that, I see, you know, this implies nothing or this implies false. I just translate nothing to false in my head. It's isomorphic to the Boolean value system, except it's at the type level. So when you're writing programs, you can actually say not some type. And then, let me see, what else did I put in here? Oh, right. Did I put that in here? Type value for context. Oh, right. Or the V-looking thing. That's interesting. If you have spent any time with logic, you'd recognize the implementation of or in terms of not and as De Morgan's law. De Morgan's law simply says, given not and either and or, you can define the other side of and or in terms of not and the other one. So if you have and not, you can get or out of it, which is what's going on here.
The down pointing V is or?
Sorry?
The down pointing V is or?
Down pointing V. Yeah.
Okay.
The normal sort of V shape, as opposed to the TD kind of thing, which is and.
Can I get you to belabor the idea of not T implies nothing? Or not T equals T
Sure.
implies nothing?
So in Scala, for example, if you have a function whose return type is nothing, it will not return. That you've explicitly said this function does not return. And again, going back to the earlier slide, non-termination is equivalent to contradiction, is equivalent to logical contradiction, right? So, so not, negation, is something implies false, whatever the thing is. Yeah.
Is that an implication or is that a type signature? Are you saying a function that takes a T
It doesn't
and
make
returns?
they're exactly the same thing. That is the whole.
But that's the syntax for a function in
Yep.
Scala?
Yes.
Okay.
Yes, it is.
Now, is
Yep.
there a Haskell analog for the nothing type?
Bottom.
Bottom? Okay. Thank you.
Right. And I forget what the actual name of bottom is in Haskell. Somebody.
Okay.
Somebody who knows Haskell can fill in that blank. But yeah, it's exactly this. It's just an uninhabited type.
Okay.
An uninhabited type is logical falsity, as far as the propositions as type lens is concerned, or the Curry-Howard isomorphism lens, which I prefer.
So would you make something of type not T?
Sure.
Why?
So for example, again, look at the implementation of or, right? The type signature for or. So what that lets me do, and right below it is a type lambda for use in a context bound. In Scala, I can say, here's a function that I want to be able to pass. Let's keep it simple. I want to write a function that I can pass either a string or an int to. And I want the compiler to yell at me and try to pass it anything that's not a string or an int. So I can literally say, you know, def foo, open square bracket, what did he call bar v bar, I'm sorry, int bar v bar string, constraining the type to be int or string. That's literally what that means. And it's admittedly weird because what you're basically asking the compiler to do is to prove that int is a subtype of int or string is a subtype of int or string, which is true, right? But if you pass in anything else, it won't type check. So again, take the propositions as types idea literally. What that means is that type checking is proof checking. So you're asking your compiler to prove that what you're passing it is or is not true.
If it builds, your theorem is true.
Yep.
So it might not terminate. I mean, Scala, like the type system is essentially Turing complete.
It turns out that Scala's type system is Turing complete, not on purpose. But yes, that is true. Just like C++'s template system is Turing complete accidentally, not on purpose.
But the compiler will give you an error. It won't. The compiler won't have an infinite loop.
It can, not with these type signatures. But you can absolutely write types in Scala that will cause the compiler not to terminate.
Okay.
Just like you can write write template programs in C++ that will cause the compiler not to terminate. This was recognized fairly early on in templates in C++, which is why every C++ compiler in the world actually has a template instantiation depth limit argument. And if you use Boost at all, you'll notice that it sets the template instantiation depth limit to 100, when the default for your compiler is probably more like 10.
These days it's more like 1024.
Yeah, it's bigger.
Requirement.
Right. Yeah, can you tell that I used to do C++ in Boost? But anyway, yeah, it's true. But this is a perfectly lovely, perfectly terminating, this just lets you say, I want to write a function that takes one of these two types, and I want the compiler to yell at me if I pass it something else. But it's straight out of 19th century formal logic. It is De Morgan's law in the type system. That's all it is. Encoding negation and encoding disjunction in terms of conjunction. And conjunction, again, you have in Scala with with. You can create a product type with anytime you want. So that's kind of cool. And here, Miles Sabin is the principal developer of Shapeless, and somebody yelled at him at one point saying, the Scala compiler is not a theorem prover. And he shot back, yes it is, just not a very good one. There's another library called Refined, a little bit less mental heavy lifting for those of you who are not familiar with formal logic. It just basically lets you elaborate types with stronger conditions or refined types. So you have an int, okay, great. Int is not very specific. What if you could say, an int that's greater than 10? Or what if you could say a string that is a valid email address, or a string that matches this regular expression? I'm not making these up. These are all actually in the refined library. And of course, you can either define literals that conform to those types, and the compiler will yell at you if the literal doesn't conform to that type. Or, given a value at runtime, like from some external input source, you can lift it into one of these refined types and get a disjunction, an either. It'll be a right if it satisfies the type constraint. It'll be a left if it doesn't. And you can handle that with your usual mechanisms for handling eithers in Scala. And so that's all using the same kind of underlying logical machinery, and it's looking through the propositions as types lens. It's just doing it at a much higher level in a more immediately practical, usable kind of way. You can use types in your program wherever you need a valid email address, and by God, it'll be a valid email address, or it won't compile, or you'll have to deal with the left side of an either from the input that you read from some web form or something like that. Okay. More controversy, yeah. So here's Dr. Wadler going back to this idea that logic is universal, and that therefore, through the propositions of types lens, types are in some sense universal. And he's maybe speculating a little bit on what would happen if we had contact with alien intelligences and things like that. But I think the thing that he wants to underscore, and the thing that I want to underscore, is that again, because multiple people come up with the same idea in different contexts at different times, it does kind of suggest that that there's something to pay attention to here. And it might be mysterious as to why, and you might have different aesthetic judgments about it than some other people, but it's worth putting some thought to. Oh, this is where, yeah, continuing that thought of universality. Here, Dr. Wadler even claims that even if the multiverse theory of quantum mechanics is true, that all that means is that the universality of logic might become the multi-universality of logic. So, some more food for thought, and people have definitely pushed back in comments on this idea. Yeah, okay. Some personal notes from me with respect to all of this. It's a big source of frustration for me. I'm the son of two teachers, elementary school teachers, but teachers nevertheless. And so I pay attention to what people are talking about in education a fair amount, and especially in our field, meaning software development, for those of you who are in this field. There's a lot of talk lately about education, and STEM education in particular, and the need to teach computational thinking. Well, what is computational thinking? And I think Dr. Wadler and Hurry and Howard before him have made a pretty good case that computational thinking is just logic. And the problem with that, as far as I'm concerned, is that logic has been part of what's called the trivium since the Middle Ages. For some strange reason, we stopped teaching the trivium. We stopped teaching grammar, rhetoric, and logic. And we veered off into other directions that have been deemed more relevant or more mind-expanding or whatever. So I would venture to opine that if you care about STEM education and you actually agree with the thesis that we need to teach computational thinking, then you are in fact a conservative. Maybe by accident, but what you're proposing is a return to teaching the trivium in our schools. And I personally think that's a good idea. And if that makes me, socially retrograde, I really don't care. And what else did I put in here? Oh, right. Yes, of course. If you want to get your kids interested in this stuff, have them read Charles Lutwidge Dodson, better known as Lewis Carroll. And of course, I couldn't resist closing with this Alan Perlis quote. The best book on programming for the layman is Alice in Wonderland, but that's because it's the best book on anything for the layman. And that's all I got. Like I said, wanted to breeze through it, and questions, comments.
Yeah, I figure we'll do maybe 15-20 minutes on Q&A about this, try and stay on topic, and then we can kind of break into whatever we're talk informally.
Right.
Great. So, yes.
So you mentioned that untyped lambda calculus has an undecidable halting problem.
Mm-hmm.
And you say that this makes it inconsistent.
Mm-hmm.
But doesn't that make it incomplete rather than inconsistent? I mean, maybe I'm thinking about it wrong, but that's what it would sound like to me.
So when it's inconsistent because you have in fact stated some specific proposition that takes, and again we have to get into the details of intuitionistic logic or constructivist logic a little bit, and that would be a pretty lengthy sidebar. But non-termination means that there is an underlying logical process that arrives at a conclusion that implies the opposite conclusion at some point. That's inconsistency. And again, to get into the details of that, we would have to get into the specifics of what is the semantic relationship between computation in any given programming language and constructivist logic or intuitionistic logic. It might be worth pointing out, for example, though, by way of elaboration, that there's a very popular proof assistant, theorem prover, semi-automated theorem prover called Coq, that is based on type theory. And so it has a full-on programming language built into it that is simultaneously the language that proof terms are expressed in, and that you can write programs that Coq can execute. And the catch there is that it is sub-Turing. It is not Turing complete, because to be Turing complete would imply inconsistency, and hey, this is a proof assistant. So there's probably the most direct example that I can think of the isomorphism between logical inconsistency and Turing completeness or non-termination, which are the same thing. And to be very frank, at this point, I've come to believe with a gentleman by the name of David Turner, who, for some strange reason, Dr. Wadler doesn't even refer to in this paper, who has argued that functional programming should be total. So he's actually explicitly argued that you do not want Turing completeness in your programming language. And the reason for that is that you generally want your functions to actually do something. And the counter argument that generally is offered is, well, what about servers, that do in fact loop forever and continue to do something? And the answer to that involves words like co-data and co-recursion and co-induction, and are outside the scope of this particular talk. But there are subterranean answers to how do you write a server.
You said David Turner?
Sorry?
David Turner?
Yes,
Okay.
if I believe I remember that correctly. Miranda was his.
Okay.
Yes,
Yeah.
David.
Mhm.
So to make a language consistent requires the absence of the ability to recurse indefinitely.
Yes.
But clearly, you can express indefinitely recursive types.
Yes.
So how does that work out?
They have to either be inductive or co-inductive. So there are so without again going off into a lot of detail that I certainly don't have command of by memory. There are patterns of recursion that are not general recursion, less powerful than that, that you do want to be able to take advantage of, for sure. The most obvious example of that, of course, is structural recursion, where we do this all the time in functional programming, right? We have some sort of base type, and then we have some inductively defined type in terms of that base type. The obvious example, of course, is list, right? So you have an empty list, you have nil, and then you have a list that is a cons of something onto nil, right? Or something onto something onto nil, or something onto something onto something onto nil, and there's your list. You can keep that up indefinitely. But any given list at any given time actually has a finite number of elements, right? Unless it doesn't, unless it's a lazy list. But that's all that means is that you're taking advantage of the isomorphism between data and computation, right? You're just lazily producing the value when you ask for it, stuff like that. But that is still an inductively defined type, and it's finite. I mean, it's recursive, but it's finite.
Yeah, there's an algorithm or a name I just read recently, and I forget it now, but it was you can do recursion as long as you can prove that it reduces.
Yep, as long as it gets smaller.
Always,
yeah.
The list always ends up smaller at each
Right.
recursion or whatever the tree.
Yeah. And it turns out there are a lot of other patterns of recursion that are even more powerful than that, and we don't have them in our programming languages for the most part. You really have to kind of push. First, you have to say, I'm going to do total functional programming. Okay, congratulations. Not even Haskell is a total functional programming language. It has partiality all over the place. Take the head of an empty list. Boom. Everybody knows that. Everybody who knows Haskell knows that. So when you say, I want to do total functional programming, not just typed functional programming, but I want to do total functional programming, you've put yourself in an extraordinarily small minority, even smaller than Haskell programmers, again. But that's what you have to do in order to be able to consistently reason about your code without running it to see what it does. And it's interesting to note that my team at Verizon OnQ, that's actually what we do. We do it in Scala, though. But we emphasize totality as well as using types and being referentially transparent. So we're in this. We're in an even more ridiculously tiny minority. Typed functional total programming, not in Haskell.
So that's a reducing recursion.
Yes, right. We get smaller and smaller and smaller.
Right.
Yeah, exactly. We can prove termination that way.
So I'd never used Coq and was interested that its programming language is total,
Mhm.
but I have used HOL, whereas since that's programmed in ML, that is clearly a partial. That is very partial. So
Well,
why would
it's-
some use Coq over ML over HOL, for example? What does it offer? What does the totality offer?
Well, what does the totality offer?
Yeah.
Soundness. But then again, all we're talking about now is the difference between the type theory, a type theory based proof assistant, and the higher order logic based proof assistant. And what Isabel
Right.
relies on is the LCF paradigm, the logic of computable functions paradigm, which is just another way of saying the same thing.
They're related. That's very
there's so basically in the Isabel or any Hall implementation,
Right.
of which there's more than one, in any Hall implementation, basically you do in fact have a type that ensures termination. That is
Is there a quick one or two sentence definition of what makes something partial versus total?
Yeah. Again, if a function is defined for all elements in its domain, it's total.
Okay.
Now, the way you express partiality depends. So typically, again, you express, in popular programming languages, all of them, You express partiality with exceptions. You know, if you can't handle some input, you throw an exception. In functional programming, what we like to do is not throw exceptions, but instead we like to, well, let's put it this way. Suppose you've got a partial function. Let's take a concrete example. Let's take the good old-fashioned factorial function, right? Typically, when you see a factorial function defined in some programming language, it's defined on int, right? Because your programming language has integers as one of its data types, okay? What's the problem with trying to define factorial on integers?
Negatives.
Negative numbers.
Yeah, right. Factorial is not actually defined for all integers, right? So if you pass it a negative number, you're going to get what?
Undefined.
Yeah, it's going to crash, right? It's going to blow up somehow. You know, it's going to stack overflow. It's going to, you know, whatever. That's how you know that factorial is partial in the integers. If your language has a natural number type, nat, you're golden, right? Because factorial is in fact defined for all natural numbers. Those of you who are a little more mathematically sophisticated would say, just use the gamma function. It's defined for complex negative numbers.
Doesn't work for negative integers.
Sorry?
Doesn't work for negative integers.
Doesn't work for negative integers.
Nope.
Really? The gamma function doesn't work for negative integers?
No, only negative, decimals, not integers.
It has asymptotes at each one.
Yeah, okay, fine. so you use a delta function and everybody goes home happy. But yeah, that's so if you want to actually reason logically about your code, if you're a programmer, then I would argue you have to use total functions. So now the question becomes, how do you make a partial function total? We already talked about one way to do that, which is to make the domain smaller, right?
Yeah.
If you can make the domain smaller, so the function is in fact defined for all elements in the domain, great. Once again, everybody goes home happy. That doesn't always work because sometimes we have to deal with the outside world, right? And unfortunately, we have to do I/O. We can't just make the CPU hotter and all that kind of stuff. So at that point, it doesn't matter what your domain is. You're talking to the outside world, and that can fail. So the other alternative is to make your codomain larger. And again, typically what that implies is using some sort of sum type. So you have an error type or a success type. You want some sort of sum type as your result type.
That's what I was trying to get to. I'm glad you went there.
Yeah.
Yeah, thanks.
Right, sure. And then what do you do when you have either an error or an actual result? Very often it's useful to have that result type be a monad so that you can actually compose these things in a logically understandable way. And that's why we talk about failure monads or error monads all the time, is so that we actually have a total function because anything that could go wrong in the function is actually exposed in the return type, and it's exposed in a way that we can then reason about algebraically throughout the rest of the program, reason about logically throughout the rest of the program. And that's why I write code the way I write code.
Yeah.
Anything else? Sorry?
Yeah.
You had another paper that you went over for the feature that was building on top of Wadler's work as propositions as types.
Did I?
Can you elaborate a little bit more on, you said it was a book that was going to be released soon by Princeton.
Oh, the homotopy type theory book.
Yeah.
Oh, it has been released. Yeah. This paper is from 2014, I think. So yeah, the homotopy type theory book is out. Yeah.
It's also an introduction talk by Gershon Bazerman, where he's just like, what is homotopy type theory?
Yeah, which is a reasonable question.
Which he taught. It's very beginner level. There's no deep stuff. It's just gives you an overview of the sense of what would you even use this for.
Yeah.
So.
Yeah.
Last question.
Yep.
What are your opinions on Haskell?
So I think Haskell is a stunning, 20-year-old achievement at this point. So it's important to remember what Haskell is. Haskell is the functional programming research community's answer to the question, what do we do about the fact that we have 5 or 6 mutually incompatible lazy functional programming languages? So there was Hope, there was Miranda, I forget what else.
Lazy ML?
Sorry?
Lazy ML?
Lazy ML, yeah. And so it was hampering research. So Haskell, it's kind of a funny parallel. Haskell came about for essentially the same reason Common Lisp did, which is that there were all these mutually incompatible dialects, floating around, and it was hampering people's ability to communicate results. That's why Haskell exists. That's also why Haskell's motto is avoid success at all costs, at which has been remarkably successful. So mission accomplished, right?
That makes it a failure, doesn't it?
No. Because people are actually using it in industry.
It's a success,
right?
and so it's inconsistent. And
this is
very bad.
But even if it fails, then it's succeeded at that. At which point,
so,
it's
right?
broken.
Yeah,
So,
exactly. Yeah.
No.
So first you have to define success. I like Haskell. I dabbled with it and it didn't take, and this is going back many years at this point. I would probably feel happier reapproaching it today than I did when I first approached it and rejected it. Two issues come up for me that continue to sort of stick in my craw a little bit. One is, I think it's a problem when you actually have two standard libraries, one with M at the end of everything and one without. The reality of the situation is that thunk bombs suck. And for those of you who actually care about the performance of your software, usually Haskell is fine, but when it's not, it's really, really not, and it's very, very deeply mysterious to track down why.
Was that in the context of parallel programming?
Nope. Nope. Just regular plain old, oh, I'm lazy, I'm building up all these things, I'm building up all these things. So now I'm actually going to execute all these things, and all of a sudden your performance goes straight to hell.
Try defining factorial in Haskell the kind of naive way, and then try a factorial of 100. You'll be waiting all day for factorial of 100.
Then I'll just throw some exclamation points in it.
Yeah, exactly. See,
Right.
Yeah.
That's what they say in the wiki.
Yeah, I just, it's interesting. There's a presentation that I don't know how many of you are gamers here, several people in the game industry. Tim Sweeney is the technical lead at Epic Games, the Unreal technology and all that kind of stuff. He was invited to do a presentation at the Principles of Programming Languages conference in 2006, where he talked about the next mainstream programming language from a game developer's perspective, and basically sang Haskell's praises, except that he said laziness is the wrong default. And basically I think a lot of people in the community agree with that assessment. It's just too hard to reason about performance and about space and time in a lazy language. Sorry, Haskell folks, but there you go.
I've never had a thunk bomb.
Well, I've been hearing from the Haskell community that we're not supposed to use the writer monad anymore because of that problem. Like it's impossible to reason about space or something.
Yeah.
It's apparently just a failed idea.
Yeah, and again, it's not that it comes up a lot, it's that when it comes up, fixing it, even tracking it down, is unbelievably excruciatingly difficult. And for those of you who are Haskell fans and want to see sort of exhibit A of something like this, I would refer you to the Dark's revision control system, which was notorious for exponential performance degradation under certain use cases that turn out to be comparatively common.
Did you say Darks?
Yes.
That's written in Haskell?
Yep. Yeah.
You've mentioned Coke a few times, and I was pleased to see that there was a talk on YouTube that actually demonstrates its usage that was put up by a smart and handsome individual who also works for Verizon on Cube, coincidentally. Seriously, I was hoping you would give us a pointer, since I think other people here might be interested in that talk that you put up there.
It's actually in the description of this event.
Oh, was it in there? Okay. Yeah. It's a bit long, but if you're interested in this kind of stuff, I would recommend.
If you're a bleeding masochist, it's 2 hours and 17 minutes.
Well, you don't have to watch it. You don't have to watch it all at once. I've only watched the first hour so far. I will get back to it, but it can be done. And if you want to see, if you want to see, no, you endorsement. No. Well, I mean, I didn't have 2 hours at that moment. That's all. But even though I didn't have 2 hours, I wanted to watch as much as I could at that moment. But seriously, if you want to see what Coke is about in action, doing a real proof with some annotation
by
Paul.
the way, it's cock. It's a perfectly good French word that means rooster.
Okay. I heard someone say Coke here, so I wasn't sure. I've heard it both ways, so
And,
that's
and
fine.
having grown up in farm country in Indiana, we called them cocks too.
Anyway,
it has
so,
three meanings.
so seriously, if you want to see it in action with Paul kind of describing what's going on, proving, what's the Cretan liars paradox, I think it is, or something like that, so it's worth your time, in addition to the surrounding stuff.
Yeah,
that we
thanks.
talked about.
Yeah, I use a little web interface to the theorem prover to work through some puzzles, some Riemann-Smolyan puzzles from one of his puzzle books, and then lead into the Curry-Howard isomorphism from there. So I think it's good, but I might be a little biased. But thanks.
And there's a bit more about Lewis Carroll in there too, which is kind of
Yeah,
cool, which,
yeah, you might recognize some of the same pictures from these slides and from that presentation.
If there aren't any more questions, I think we might wrap up Q&A. Thank you, huge thank you to Paul. Thank you all for coming. This wouldn't be a meetup if nobody came. If you enjoyed it and would like to come back, please do. If you hated it and would not like to come back, I sure would like you to tell me why. And if you'd like to present something that you've read or like to read something, I could point you in the right direction. Yeah, so thank you all for coming. I think there's still a little more pizza, maybe. There's some drinks, but yeah, thank you for coming.
Thanks, everyone.